Hey, welcome everybody. Alright, we're back to working with trigonometric identities, and in this video we're going to be using the trigonometric identities that we've been learning in order to help us solve some more trigonometric equations, some more difficult trigonometric equations. The thing we're going to focus on here is using substitution and factoring techniques in order to solve trigonometric equations that include two or more trig ratios, meaning that you would have an equation as a sine and a cosine, or a sine and a tangent within it. Alright, you'll see those momentarily. Now there's several identities that we're going to need to be familiar with, and I would suggest having these written in front of you. Have your formula booklet in front of you with all these written in them if you've got that. You'll need to know your cosine double angle identities in order to solve the equation that we're solving. You'll need to know your sine double angle identity. You'll need to know the sine squared theta plus cosine squared theta equals 1 identity, as well as what that is when you get sine squared and cosine squared by itself. And we'll need to know the identity tangent theta equals sine theta over cosine theta. Alright, now, not guaranteed we'll use all of those in all the problems that we're working through, but those are the ones that are in your tool belt, so to speak, that IB is going to expect you to know, up to this point at least. So, let's get on to solving some equations. Now, we're going to go ahead and solve this equation here on the interval from 0 to 180 degrees. The sine theta minus cosine theta squared equals 1. And you see that we've got the two different trig ratios like I was talking about, a sine theta and a cosine theta. And we've actually worked with equations that have a sine and a cosine in them before, but we treated them a very specific way. And I want to explain briefly why that way is not going to work here. What we've done before with equations that have a sine and a cosine in them is we've gone ahead and divided everything by cosine theta. Now, I know we couldn't do this anyway because of the exponent, but just humor me for a moment. Suppose that we could. Regardless of that exponent, if I divided everything by cosine, I'd have to divide both sides by cosine, and that wouldn't actually accomplish the trick of getting us down to one trig ratio. Because while this would become a tangent theta, and this would become 1, now you would have a 1 over cosine. You would still have a trig ratio here and a trig ratio there, and you're no better off than where you started. So that is not going to be the way that we're going to handle this. Also, it turns out it's not going to be very helpful for us to take the positive and negative square root of both sides, even though that's allowable, certainly, because we'll still run into the same problem where then we have to figure out a way to try to get these two trig ratios down to 1, and it won't be a simple way to do it. What we're going to do is we're going to go ahead and square this binomial, and it's really going to be cool the way this works out, actually. All right, so when you square a difference, remember your a squared minus 2ab plus b squared pattern, meaning that we're going to get sine squared theta minus 2 sine theta cosine theta plus cosine squared theta equals 1. Now you're probably thinking, Mr. Klinkerman, this looks no easier than what it was before. And I would say, yeah, it doesn't look any easier, but haha, a couple really cool things have happened here. One of those is that, I hope you'll notice we've got this. We've got a sine squared theta plus a cosine squared theta in our equation. And if we look back at our identities, we know that sine squared theta plus cosine squared theta is equal to 1. And so we're going to be able to make a substitution. We can substitute what I've highlighted with a 1. So we'll now have 1 minus 2 sine theta cosine theta is equal to 1. Now don't tell me that doesn't look easier. And it's going to look even easier here in a second, because now we can subtract 1 from both sides, and we just end up with negative 2 sine theta cosine theta is equal to 0. Alright, now the fact that there's a 0 over here means there's a couple of different options we could use. We could actually just set the sine of theta equal to 0 and the cosine of theta equal to 0 and solve right now. But I'm trying to show you how to use double angle identities and other identities to help you out. And it turns out there's another one that we're going to use right here. Notice that in this negative 2 sine theta cosine theta, we've got a 2 sine theta cosine theta. How is that relevant? Well, 2 sine theta cosine theta is just equal to the sine of 2 theta, isn't it? So we can further simplify this equation into this negative sine of 2 theta is equal to 0. So you see how we were able to get this down to a single trig ratio, now we only have a sine, by using identities and substitution. All right, doesn't work 100% of the time, but really cool when it works, and you're going to see a lot of problems where it works, both on my test and your IB test as well. All right, so now we're almost to the point where I want to solve. Let's go ahead and get rid of this negative sign. Let's divide both sides by -1 and get sine of 2 theta is equal to 0. And then before we actually look on the unit circle and see where are the angles whose sine is equal to 0, keep in mind that now we're dealing with 2 theta, and so we have to make sure we know what range of values 2 theta has to fit between. Since theta is between 0 and 180 degrees, that means that 2 theta would be between 0 and 360 degrees. So we want to look over the entirety of the unit circle from 0 to 360 and determine where would the sine equal 0. And that's going to be in 3 locations. At 0 degrees, you get a sine that's equal to 0. At 180 degrees, and then again at 360 degrees. And so all of those angles tell us what 2 theta is equal to. And now that we know what 2 theta is equal to, we can just go ahead and divide everything by 2, that's a degree sign, and that'll give us 0 degrees, 90 degrees, and 180 degrees as the 3 solutions to our equation that are between 0 and 180 degrees. All right, really cool how you can look for trig identities to help you make a trig equation easier to solve. All right, let's look at another one. Looks super complicated here. We're again solving for angles theta between 0 degrees and 180 degrees. And you see we've got cosine and a sine, and we've got a quadratic expression right there. Oh my goodness, how difficult is that, huh? Not all that bad, actually. All right, now, you might say this, Mr. Klinkerman, I noticed there's a sine of theta in this first term, and there's a sine of theta in the second term. Can't I just go ahead and divide both sides by sine theta, and then I'll only have a cosine squared theta in the equation? And I would say, yes, you're right. But there's a danger in dividing both sides of the equation by a trig ratio. All right? It gets rid of some of your solutions many times. Now, we've seen where it hasn't in the past, but what's going to happen is we're not going to find all the solutions if we divide everything by sine of theta. But your observation is not in vain, because what we can do instead is we can use factoring. This is a common factor for our 2 terms, so we can factor it out. Well, let's do that then. Factor out the sine theta. And then in the first term, that will leave me with everything that I didn't highlight. 2 cosine squared theta would remain. And then we're factoring sine theta completely out of itself, so that's going to leave us with a 1 in the second term. All right, excellent. Now, when you're factoring, by the way, always make sure that you've got a 0 on the other side of the equation. Otherwise, it's pointless. We know if 2 numbers multiply to give us 0, that one of these numbers has to be equal to 0, and so we can solve. That doesn't work if this is not a 0 on the other side. All right. Now, what we're going to do is we're going to set each factor equal to 0. And even though we have more than one trig ratio, each of our equations that we create when we separate the factors is only going to have 1 trig ratio. However, before we do that, even though we've done enough work to be able to solve the equation here, I'm going to use another substitution. You see this 2 cosine squared theta minus 1 right there? Well, let's go back and look at our list. That happens to be equivalent to cosine of 2 theta. And so I'm going to substitute cosine of 2 theta in place of this expression right here. Oops. All right, that's more like it. So we now just have the sine of theta times cosine of 2 theta is equal to 0. And we'll just separate each of those factors and set them equal to 0. So sine of theta is equal to 0. And the cosine of 2 theta is equal to 0. Now, kind of interesting here that in one equation we just have a theta, and the other one we have a 2 theta. So when we're looking on the unit circle for this one, we're only going to look between 0 degrees and 180 degrees. When we're looking on the unit circle to solve this equation, we're going to look between 0 and 360 degrees. Now let me color code what we're doing. I'm going to, whoops, that's not what I wanted. I'm going to go ahead and highlight this first equation as just what we're trying to solve, and I'm going to show you on the unit circle where its solutions are. Remember, since that's just a theta, we're looking between 0 and 180 degrees. for all the locations where you can get a sign that's equal to 0. And we just saw that in our previous problem. We know at 0 we get one of those values, and we know at 180 degrees we get one of those values. And this time, since we're only looking between 0 and 180, that's going to be it for that. So that equation is going to tell us that theta could either be 0 degrees or 180 degrees. Now let's look at the other equation. I'm going to highlight it in yellow, and then I'll put some yellow points on the unit circle so you can follow where the solutions are coming from. So since that's a cosine of 2 theta, we're going to look between 0 and 360 degrees. That's the range that we're looking at. And we're looking for where the cosine is equal to 0. Well, cosine would be equal to 0 first of all at 90 degrees, and then at 270 degrees, and that's it between 0 and 360. So that equation tells us that 2 theta can equal either one of these values. Whoops, not that one. 270 degrees. And so we have two more values of theta now, 45 degrees and 135 degrees. And I'll just write all four solutions that we got in total in one line. All right, again, the substitutions helped us out, and factoring helped us out in this equation. All right, let's go for another here. More trig ratios, or multiple different trig ratios here. And we've got one that's been squared. We've got a multiple angle. Man, this looks tough, huh? All right, actually the thing that's difficult about this one is that there's one more principle that's at work here that we haven't talked about. Not only do we have different trig ratios, but we have one trig ratio that has just an x and another trig ratio that has a 2x in it. That worked out fine here where the equation was written in factored form because we could just set each factor equal to 0. But here, where these different angle measures are in different terms altogether, that's not going to work for us. So we either need to make it so that both of these expressions have a 2x in them, or they both have just a regular old x. And what's going to actually be easier to do is to make them both have a regular old x. And the reason why I say that is because we can take this cosine of 2x and use whatever our double angle identities in order to make it just have an x. But we don't want to just randomly pick one of those double angle identities. What's the other equation, trig ratio that we have here? A sine squared. So if we're looking at our trig ratios, how about we use this one right here, where we can say the cosine of twice an angle equals 1 minus 2 times the sine squared of that angle. There's the substitution that we're going to use. So replace this with 1 minus 2 sine squared x. Not that tough, right? Now let's clean this equation up a little bit. Two things that I'm going to do. First of all, the parentheses I just used to show you where I substituted this value. But since there's just basically a 1 in front of them, there's no distribution to do, we can kind of ignore the parentheses. And we would like our sine squared x's to be on the same side of the equation. Now these are like terms. If I have a sine squared x and a sine squared x, those are like terms, and I can add them. So let's add 2 sine squared x's to both sides, and that 1 sine squared x plus 2 sine squared x equals 3 sine squared x. All right, and then on the right side we have 2 plus 1 is equal to 3. All right, now no more substitutions that we're going to be able to do. This is a quadratic. The way we're going to be able to solve this then is just go ahead and divide both sides by 3. And then we'll take the positive and negative square root of both sides. And so we'll get sine of x is equal to negative 1. And sine of x is equal to positive 1. No double angles involved, so we're going to look on exactly the interval that was expressed to us in the directions. Let's take a look at the first equation. The sine of x would equal negative 1. Only one spot on the unit circle, right there. And if we're talking about between negative pi and positive pi, well, between negative pi and 0, this would be negative pi over 2. And then we're not going to get back to that as we go from 0 to pi. So negative pi over 2 is the only solution on our indicated interval for this equation. All right, now looking at this equation, let's go ahead and put solutions in orange. The only place on the unit circle where you have the sign that's equal to 1 is, of course, right there. Now, if we're looking between negative pi and pi, starting here, from negative pi to 0, we never touch this. From 0 to pi, we only touch that at pi over 2. And then any coterminal angles are going to get us something too large here. So only pi over 2 is going to satisfy that equation. So we can say that negative pi over 2 and positive pi over 2 were the solutions to that trig equation. All right, so again, using a double angle identity or an identity in general helped us solve. We're going to do one more in this video. All right, now we're going to use the same interval that we did on the previous problem. We're going to go from negative pi to pi. Forgot to put that in the directions here, but that is the plan. And you see in this equation we've got a cosine squared x and a sine squared x. Now, I'm going to give you this piece of advice. Anytime you've got an equation that has a cosine squared x and a sine squared x in it, it is a beautiful thing to get them both on the same side of the equation. Great things happen when you get cosine squared x's and sine squared x's on the same side of the equation. And in fact, I'm going to do two things here. To make that occur, I'm going to subtract sine squared x from both sides, but I'm also going to go ahead and subtract the square root of 3 over 2 from both sides. And that will give us this. Cosine squared x minus sine squared x equals negative square root of 3 over 2. Now, why am I saying it's a beautiful thing when you get the cosine squareds and the sine squareds on the same side of the equation? Because two things can happen. Let's go back and look at our identities. Either you have a sine squared plus a cosine squared and you can replace it with a 1, or you might get a cosine squared minus a sine squared and you can replace that with cosine of 2 theta. And this is what we have in our problem, is we have a cosine squared x minus a sine squared x, so we're going to be able to replace it with a cosine of 2x. All right, so this quantity right there can become cosine of 2x. Now for our solutions. I told you that we were using the same interval for x as we were here, from negative pi to pi, but now we're dealing with 2x, so 2x is going to be anywhere from negative 2 pi to positive 2 pi. So we're going 2 revolutions around the unit circle. Now if we start at negative 2 pi, which is right here, and we go to 0, well, there are a couple places where we'll get the negative square root of 3 over 2. Actually, what I ought to do is just look for where is a cosine negative square root of 3 over 2. That happens about right here and right there on the unit circle, right? Now let's figure out what those angle measures are from negative 2 pi to positive, or to 0. Those values are negative 5 pi over 6 there, and negative 7 pi over 6 here. Now if you're looking positive from 0 to 2 pi, might have actually been an easier way to start, but they both work. This is 5 pi over 6. And of course this is 7 pi over 6. Now any other angles are just going to be outside of the range of values. All right, you can look for the coterminal angles, but we found the ones that are going to work. Great, so we know what 2x can be from least to greatest. It could be negative 7 pi over 6, negative 5 pi over 6, positive 5 pi over 6, and positive 7 pi over 6. You could just use some plus or minuses to group these a little more nicely, if you like. And so now we're going to go ahead and divide by 2, or rather multiply by 1/2, since we got all these fractions over here. And we can say then that x could be either plus or minus 7 pi over 12, or it could be plus or minus 5 pi over 12. So you've learned how you can substitute in trigonometric equations using either double angle identities or other identities that we've learned so far in order to make equations simpler to solve. Thank you everybody for your hard work and attention. Goodbye.